Hi guys, today we will be looking at logarithms. This video will be a basic introduction to logs, and I will show you some common rules in this topic and prove the log identities once, so you can understand the logic behind the formulas better. Now logarithms is basically another way to write exponents. However, in logs, we make the exponent the subject of our equation. So let's say if we have something like log base a of b, this basically means that how many times does a have to multiply itself in order to become b. So if we let this expression be something like a star, now this means that a to the power of a star would equal to b. This is the simple definition of logarithms. So here are some examples. What is log base 2 of 8? We know that 2 to the power 3 is equal to 8, so therefore the answer would be 3. So what is log base 5 of 25? We know 5 squared is equal to 25, so therefore the value of this is simply 2. So now that you have a basic idea of what log really is, let's move back up. You might have noticed that the exponent is actually equal to the whole logarithm expression. Since log base a of b is equivalent to the star, we can generalize this into something like a to the power of log base a of b equals b. Now log functions and exponential functions are inverse functions, and so they can be cancelled out. And hence, this expression equals to b. Another rule is that log base a of a to the power b equals to b, since a has to multiply itself for b number of times in order to become a to the power of b. So allow me to show you some more examples. What is the value of log base 3 of 9? We know that 3 squared is 9, so the answer to this is simply 2. What is log base 7 of 7 squared? Using the rule I just mentioned, we know our answer is simply 2. So what if we have log base 5 of 125? We can rewrite this as log base 5 of 5 to the power 3, and we get 3. So another important thing I have to mention is this. So we have log 1000. Now you might be wondering what is the base of this logarithm. If you don't see a base here, it implies that the base is 10. Because this is the standard base of logs, you don't really have to write that out. So we know that 10 to the power 3 is equal to 1000. We know the answer to this is simply 3. Another important concept is the range for the base and argument of a logarithm. The base of a log has to be a positive number that is not 1, while the argument has to be a positive number as well. 0 to the power of anything is 0, well obviously unless it's 0 to the power 0, then that is undefined. And 1 to the power of anything is 1. Therefore we do not consider 0 and 1 as bases for logarithms. What if we have a negative base? Well, we would know certain values, such as negative 2 squared is 4, and negative 2 to the power 5 is negative 32. However, when the exponent is in an integer, such as negative 2 to the power of a half, that would be equivalent to the square root of negative 2, which is obviously an imaginary number. So when we have a negative base, when the exponent is not an integer, it would involve imaginary numbers. Therefore, in conclusion, we do not consider logs with bases 1, 0, and anything that is smaller than 0. So now that you know the base of a log has to be a positive number that is not 1, when we have a positive number, no matter whether the exponent is negative, 0, or positive, we would always get a positive output. Hence the argument of a log is always larger than 0. So now let's move on to our log identities. In our first law, it states that log a plus log b equals to log a times b. So two logs with the same base added up together would equal to their arguments multiplied together. Firstly, let's let a be equal to 10 to the power of m, and b be equal to 10 to the power of n. Our left-hand side would look something like log 10 to the power m plus log 10 to the power n. If you still remember the rule I just mentioned, it is log base a of a to the power b equals to b. So our left hand side would simply be equal to m plus n. As for our right hand side, we can simply add up the powers, and there we go, we have our first identity proved. Our second identity is log a minus log b equals log a over b. So basically, it's the subtraction between two logs with the same base, and that would equal to their arguments divided by each other. So our first steps are very similar to the last identity, and the left hand side would simply be equal to m minus n. As for the right side, we can subtract the powers, so we get m minus n as well. So here is our third identity, which is the power rule. We can pull down the power of the argument of a logarithm like this. So we can expand the left hand side as such, and by using the first identity, which we also call the product rule, we will eventually get what we have on the right hand side. Just make sure that the power here is part of the argument, but not outside the whole log expression. And last but not least, it is the change of base formula. So we can rewrite log base a of b as such, and there's a change in the base of the logarithms. Let b be equal to a to the power c, and using the rule I mentioned, the left hand side is simply c. We can utilize the power rule on the right hand side, and log a can be cancelled out, and hence we have our fourth identity. The special thing about this formula is that you can insert any base here as long as both log expressions share the same base. And here are some random practice questions that I made myself. Well, most of them. You can feel free to pause the video and give them an attempt. You can also type up the answers in the comments. If you get it correct, nobody would reply to it, but if you get it wrong, eventually some math nerds will come correct you. I know this video is kind of boring, so thank you so much for watching it. Again, thank you so much for watching this video. Please give it a like, subscribe to my channel, and share it to your friends who seriously need some help in math. I will provide solutions to some of the questions here in the next video, and hopefully it will be an interesting one.